Hello, everyone. So we're going to talk about radiation, and that is heat heat transfer by light. And we're not saying what sort of light, if it's visible or anything. It's just energy radiates away as electromagnetic waves, as light. So the astronomy class has talked about this a fair bit, and the gist of it is and this is why I focused on power, is that you can always do the heat is power times time. So the power depends on a certain set of things. It depends on how reflective an object is. This is what's called black body radiation. Is if we want to set the temperature of an object based on the energy it receives or the energy it emits, then we have to know something about it. All right. So one thing that obviously matters is the area. Light is emitted from the surface of an object, so the surface area matters. There is a constant here, sigma, which I'll get into in a minute. And then there's this E, the emissivity, which is essentially how unreflective, how absorpting is the object. So this is the thing. All objects radiate. All of them. All of them radiate because of their temperature. So imagine an object like a black car. You got a car hood, it's black, and you got another one that's painted silver. Which one feels hotter to you? If you just hold your hand over it, don't touch it, just feel. It's probably the black one. The silver one probably doesn't feel as hot. And what's going on is when you have an object, you have either light coming in or light going out. The light going out is based on the temperature of the object. All right. The light coming in is based on the temperature of some other object further away. But the gist of it is you have energy going in and energy coming out. But if it's reflective, what if the energy coming in just reflects? So E here is saying how much of this light does it get absorbed? And it's a number between 0 and 1. 0 is a perfect black body. Sorry, 0 is a perfect mirror. And 1 is a perfect black body. And the name of this comes from scientists, when they were studying this problem, they imagined an object that absorbed all of the light that entered on it. So like a box, and light goes in through a hole in the box, and then there's no way for it to reflect back out. And so it gets absorbed by the material. And they asked, if you looked in that hole, what it would look like. And they realized that the object has a temperature and it's got to radiate. And if it were mirrored everywhere, then the light would have to be able to get back out. So you wouldn't see this re-radiated energy. So it's got to depend on the temperature as well. And when we look at the temperature of an object and the power radiated, we realize that it is the fourth power of the temperature. And this temperature must be in Kelvin. You cannot use degrees Celsius here. You don't have a choice. Because it is an absolute changes in temperature, you can use Celsius. Actual temperature, absolute temperature must be in Kelvin. All right, the sigma here is what's called the Stefan-Boltzmann constant, and it's just a constant that makes the units work out. And it is easy to remember, 5.67 times 10 to the minus 8 watts per meter squared, takes care of the area, and Kelvin to the fourth takes care of the temperature. Okay. So let's see. This is, for your information, this is page 576. So we're going to look at some problems here. Now, the big thing about radiation is, one, power in equals power out. If you have an object at a constant temperature. And the second is power depends on the temperature of the emitter. So, for example, let's say I stand in front of a fire. So here's a fire. And then here I am, right? There's two sets of radiation. The fire, so there's logs down here, and they're burning. The fire radiates, and we'll call that P of the fire. But I also radiate in all directions. So there's lots of energy coming in from the fire, and then I'm radiating out into the rest of the room. So we can ask what my body temperature might be. And we'll ignore the fire for a minute. Let's just look at, so my temperature is 37 degrees Celsius, which is 273 plus 37 is 310 Kelvin. Now I'd like to know how much I radiate in heat. Now, emissivity for people is approximately 0.6. We don't have to use that, but we'll throw it in here. So the power is going to look like 0.6 times sigma, and then a person's surface area is about 2 meters squared. And then we'll have 300, so we'll do A is 2 meters squared. 310 Kelvin to the fourth. And this is one of those things where students have a hard time figuring out how to do the fourth power on their calculator. And what I recommend is 310 Kelvin, square it, and then square that. That's the easiest way. If you're going to do it another way, you have to make sure you're getting it right. And I will tell you that 310 to the fourth power is 9.2 times 10 to the 9. So if you get it wrong, you're going to have problems. You're going to get your numbers wrong. So what I get out of this is our power is about 630 watts. So as a living organism, you have to find 630 watts to account just for how much you're radiating out. So let's say in an hour, let's go up here. So power is 630 watts. Let's do a day. All right, so one day, the energy per day is going to be 630 watts times 86,400 seconds, and that is 54 times 10 to the 6 joules. Okay. Now, we're going to convert this to calories, And 1 calorie is 4.186 joules. So we're going to divide by 4.186. And this is 12 times 10 to the 6 calories. Now, that's not food calories, right? That's going to be the calories defined in chemistry to heat a bit of water. A food calorie is 1,000 of those. So it's going to be 12 times 10 to the 3 kilocalories. That's the food calories. That says 12,000. That's obviously not right, but it's in the ballpark. Right? We've done something a little off in our calculation. Right? Maybe our surface area is 1 meter squared. Maybe we're not always at the same temperature. Maybe our emissivity is different. Maybe we're insulating. We wear clothes all the time. The gist of it is that on the ballpark, the food that we eat, aside from doing all of the bodily functions that we need to do, also has to replace the heat that is being radiated out. Of course, there is one other thing we didn't consider. If I go back to the picture that we have here, the environment's radiating onto us. So let's look at that. All right, so here we are. We're in a 20 Celsius room, which is 293 Kelvin. Energy's coming in onto us. How much energy can we recover there? Well, our power is going to be E sigma A T to the 4th. So we'll do our estimate 0.6, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4th. 2 meters squared, 293 Kelvin to the 4th. All right, the power that we absorb is based on the emitter, which is the room, which is 20 degrees Celsius. And so this, if we calculate it out, 293, we get a big number. This is 7.4 times 10 to the 9. So we'll get that times by 5.67 e to the 8 times 2 times 0.6. We'll recover 501 watts. So the net power, what we actually lose is 630 minus 500 is 130 watts. Right? And then power is 130 watts. So the heat is going to be 130 times 86,400. That is 11 times 10 to the 6 joules. Divide by 4.186. That is 2.6 times 10 to the 6 calories, which is 2,600 kilocalories, or food calories. A diet should be roughly 1,800 calories. So our number's a lot better. The idea is that we're in warmer environments, perhaps. We're insulated, and we're also using some of our energy to do bodily functions. But the gist of it is, in the ballpark, a lot of the energy a person uses is lost as heat and has to be recovered or insulated against. So that's why people eat more when it's cold. That's why they dress warmer when it's cold, so they don't have to eat as much. Right? That's the gist of radiation, and that's the key here is going back through this. All right, you have to account for the energy input as well as the energy output. All right, so in question 4, we want you to talk about the energy that the surface of the sun radiates. That's one way, is this one calculation. So is number 5. We're talking about um, number 5 is a light bulb, but number 6 is, so if I go to the last page I have here, actually let's add one more. All right, so number 6 is blacktop road. So let's put in a road. Come on, put in a road. Come on. What's wrong with this thing? Okay, so put in a road. All right, there's a road. And from the environment, say from the sun is 800 watts in, and the radiation out is 800 watts. So I just find the temperature of the blacktop. Right, well, this is power is all right. So if it's balanced like this, the 800 watts in is coming from some environmental temperature, and the energy out is the same. And you should be able to find an equilibrium temperature. So it ends up being one calculation probably. But that's the gist of it. So that is conduction and radiation. I hope you like these videos. Particularly, I hope you like this style. I may do work on paper or on Blackboard someday, but in general, this seemed to work okay. Let me know if there's any problems. Obviously, my handwriting is I'm getting used to things. So, yeah, let me know if you have any questions. Please email me. Uh, you know, contact me however you can, and we'll see how things go.